My name is Alex, and I'm going to introduce you to AIFARMS, an exciting project funded by NSF and NIFA and one of the AI institutes in the US. The goal of AIFARMS is to advance artificial intelligence for future agricultural resilience, management, and sustainability. I'm very excited to be part of this institute and help as one of its associate research directors. The institute supports about 40 scientists, which are all eager to advance AI in agriculture. Thanks a lot to NSF and NIFA for their support of this unique endeavor. On the ag side, we have an amazing number of luminaries. I'm not going to read out all the names, but it is important to note that they provide amazing guidance on what are some of the fundamental struggles that we are going to face in the next few decades. On the AI side, we have PIs from computer vision, robotics, and controls, machine learning, and edge machine learning for sensor data. Here at CVPR, you'll surely find Narendra and Saurabh. I also want to highlight Vikram, who is leading this gigantic effort. AIFARMS also benefits from an amazing team focusing on policy, education, and outreach. Let me tell you a bit about the ongoing research, which we divided into 6 thrusts on autonomous farming, livestock systems, environmental resilience, soil monitoring, technology adoption, and education and outreach. You can imagine that a lot is happening every day in AIFARMS, and I have nowhere near enough time to discuss all the ongoing research in a meaningful way. I focus on the first 2 thrusts for today and summarize other thrusts by discussing unifying AI challenges. If you happen to be interested in a specific topic, please reach out and I'm more than happy to connect you with the right people. All right, let's get started with thrust 1 on autonomous farming. The goal is to use agbots to increase sustainability and resilience. As you can imagine, there have been quite a few efforts over the years to achieve this goal. Important challenges include autonomy, logistics, and also cost. The goal of autonomy is commonly divided into 5 levels. Importantly, simultaneously, we aim to reduce the cost per acre of deploying those agbots. For this, Katie and other researchers on the team have identified challenging goals, which they grouped into 5 levels: hands-off, eyes-off, mind-off, monitoring-off, and development-off. These levels roughly determine the minimum time between interventions. To illustrate this, we can look at an agbot from Girish's team. The bot is accurately following the lanes. Towards the end, it makes a turn, and for this, it leverages GPS, LiDAR, and INS sensors for localization and identification. It eventually successfully finds the next lane and continues the job. However, use of LiDAR also has shortcomings. LiDAR doesn't work well for small crops and occlusions. And this is where all of you could come in and help. Computer vision can provide useful additional information here. In a recent project, Saurabh, Girish, and others have devised a crop follow algorithm, which is based on a truncated resonant architecture. I'll skip the details here and encourage you to reach out to them with questions. But I want to highlight that to train the CNNs, they labeled 25,000 images in corn, of which 28% were early season and 72% were late season. The differences in appearance between early and late season from the front camera can be seen in the images. In addition, to study the generalization of the trained network, they labeled 10,000 images of early and mid-season soybeans, as shown here. Soybeans vary greatly in appearance compared to corn, and so it's an ideal test for generalization. There is an amazing data set, which hopefully provides a lot of opportunities to test different areas. Keep an eye out for this. I'd also argue that agbots need to not only analyze the current situation. Beyond, they also need to anticipate what is about to happen. What do I mean by that? Consider the example shown on this slide where 2 kids hassle each other chasing a ball. Humans passing by would be quite cautious, wondering whether the kids step aside and yield to oncoming traffic, or whether the kids run into the middle of the road without checking. We wonder about it using a mental simulation to imagine possible future scenarios. some of which have extremely unfavorable outcomes. I don't think at this point we have computer vision systems that are able to imagine complex future scenarios like the one illustrated on this slide. To get there, I think we need to combine the vision of neuroscientists David Marr and Rodolfo Linas and Kenneth Grape. They argued that a creature must anticipate the outcome of movement to navigate safely. We are referring to this as learning to forecast. The goal is to develop a system to forecast object representations given an egocentric image sequence which shows the past. For instance, the images shown on the right. Note that the observer obviously may move too. To address this, we need to first identify what are meaningful representations to forecast. A lot of representations have been considered in the past. More sparse representations like trajectories or bounding boxes, but also semantic segmentation, which, however, doesn't disentangle individual objects. Also, instance segmentation, which doesn't provide any information about the background. Alternatively, one could consider forecasting the entire image too. In a collaboration with folks at Niantic, we, and a lot of credit goes to Colin, Grace, and Michael, studied panoptic segmentation as a suitable representation. We'll present this work at CVPR 2021, so please check it out too. We think that panoptic segmentations, which represent both foreground things and background stuff, are the right decomposition for forecasting. Specifically, panoptic segmentations can handle separate motion models for different components. The appearance of things changes due to their respective movements and due to the camera movement. Meanwhile, the appearance of stuff changes just due to the camera movement only. Let's specify this task more formally then. Given a series of T RGB frames, the task of panoptic segmentation forecasting is to anticipate the panoptic segmentation that corresponds to an unobserved future frame at a fixed number of time steps f from the last observation recorded at time t. Each pixel in the panoptic segmentation is assigned a class and an instance ID. We developed the first panoptic segmentation forecasting method. It differs from prior semantic or instance segmentation forecasting approaches that either do not predict instances or do not predict dense scene semantics. Specifically, forecasting for every object instance is done independently. Similarly, we also forecast the background and subsequently aggregate the information. For accurate forecasting, we study both active and passive scenarios. In active scenarios, we know the camera position while we don't have this information in the passive side. Let's dive into each of these components in more detail. As mentioned previously, one should expect foreground things and background stuff to move differently. To exploit this knowledge, we first run semantic and instance segmentation on the input images. Detected instances are processed by the foreground model, and stuff semantics are handled by a background model. To forecast the instances, we first build instance tracks using a tracker. Next, for each tracked sequence, we feed the corresponding instance bounding boxes and appearance tensors into an RNN-based encoder-decoder model. It additionally takes camera motion into account. We then predict the final mask using a mask prediction head. In the things branch, we represent an instance using two components: a bounding box representing its location within the scene, and a feature tensor, which represents its appearance. A final mask forecast is obtained by inputting the appearance tensor into a mask prediction head, which produces a fixed size output mask. The mask is scaled using bilinear interpolation to fit the target bounding box. For stuff forecasting, as previously mentioned, we assume camera movement to be the important factor. Hence, for each input frame, we backproject the pixel locations corresponding to the stuff classes. Apply a transformation corresponding to the camera motion, and reproject the points providing their locations in the target frame. Due to possible sparsity in the reprojected point clouds, as well as occlusions due to foreground components, this reprojection isn't complete. Hence, we concatenate the reprojected points from each input frame and pass them through a refinement model, which outputs a dense background stuff forecast. To produce the final panoptic segmentation, we combine the foreground and background forecasts. For this, we simply assume that all foreground objects are located in front of all background objects, which we found to be reasonable in most cases. Thus, we paste foreground instances in order of decreasing predicted instance depth on top of the background to obtain the final panoptic segmentation forecast. Using this model, we studied two scenarios. The active scenario, where the model has access to the planned motion of the autonomous agent, and a passive scenario in which the camera is controlled by an external agent and hence the model does not know the future motion. To handle the passive case, we use a GRU to predict the future camera motion as a function of its past movement. We model camera motion in terms of the speed and yaw rate of the vehicle to which the camera is attached. To evaluate the approach, we use the cityscapes dataset, which has been used in prior work for semantic and instance forecasting. It contains 5,000 sequences of 30 frames each, where annotations are provided for the 20th frame only. To be consistent with prior forecasting work, our primary evaluation is on the validation dataset. We use every third frame as input, and we evaluate in two different settings. Short-term anticipates the third frame into the future, and mid-term anticipates the 9th frame into the future, where the target frame is always the 20th frame of the sequence. To assess, we use standard panoptic segmentation metrics. This involves first finding matches between ground truth and predicted segments, where matches count as true positives if the IOU is larger than 0.5. Using these matches, we compute the metrics. Segmentation quality is the average IOU of matches. Recognition quality is the F1 score over matches. And panoptic quality is the product of these two. Metrics are computed per class and then averaged to produce the final score. We use the following baselines. The Panoptic Deep Lab Oracle model evaluates panoptic segmentation quality on the target frame and represents an upper bound to our results. We also apply Panoptic Deep Lab to the most recently observed input frame, which represents a model that assumes no camera or instance motion. The flow baseline warps the panoptic segmentation analyzed at the last observed frame using optical flow computed between the last two observed frames. Finally, the hybrid model fuses predictions made by the best performing semantic and instance segmentation models we were able to obtain from prior work. Let's look at some qualitative results. In the top row, we show the most recently seen input frame. In the bottom row, we show forecasts 9 frames into the future, overlaying the corresponding image. Let me emphasize that we don't observe the image shown on the bottom row, but only frames prior to the one shown in the top row. On the left in the bottom row, we show the most accurate baseline. The results of our method are illustrated on the bottom right. We observe the model to perform well in cases where forecasting is reasonably easy. It struggles in harder cases, like turns, where a significant fraction of information is unknown. Quantitatively, we outperform all forecasting approaches on all metrics for both settings. These improvements demonstrate that the model better captures the motion of all scene components, including background stuff and dynamic foreground planes. The relatively low performance of flow demonstrates that simple linear extrapolation of per pixel input motion cannot sufficiently capture the scene and object movement. Additionally, the gap between the approach and hybrid on things panoptic quality grows between the short and midterm setting, which shows the strength of the model at anticipating object motion at longer time spans. Please check out the paper for many more results and ablation studies. To summarize the presented efforts of this first AIFARMS thrust, I'd argue that we are making a lot of progress. But quite some work remains to also succeed at a cost-effective autonomous airport. Let me now turn to thrust 2 on livestock systems. The goals are to identify, track, and count livestock like pigs, to estimate livestock health, and also caretaker activities. For this, an exciting camera system was installed recently. And researchers are looking at detection and tracking techniques, both locally within a camera and globally across cameras. Beyond tracking, segmentation is also of interest, as well as location and direction estimation. While this is more coarse-grained, ag researchers also care about accurate estimation of physical parameters, which could possibly be inferred from 3D meshes. This is particularly challenging, and we are trying to benefit from simulators here. There has been a lot of impressive work in the past on this, which I unfortunately have to skip in the interest of time, and I apologize for this. I mostly focus on using simulators for 3D tasks, which is work led by Yuan Ting and Jia Hong. They present this work in detail as an oral at CVPR 2021. For 3D shape reconstruction, given as input an image or a sequence of frames, we want to predict the 3D shape of the object that appears in the image or the frames. This is an important research problem for 3D understanding and has applications beyond the AIFARMS, for instance, in augmented reality, gaming, and 3D object recognition. However, annotating this form of 3D data is extremely expensive, as you can imagine. So can simulators come to the rescue? To study this, we create a 3D video dataset capturing diverse and dynamic shapes. We refer to this data as SailWAS 3D, as it extends our earlier semantic, A-model, instance, level, video, object, segmentation data. As a simulator, we use the game GTA 5, which offers good visual quality. There are also plenty of scenarios in the game, and different weather and lighting conditions too. Importantly, by placing hooks inside the graphics pipeline, we can get ground truth annotations. For example, for this video clip showing two men getting out of a car, we obtain the mesh data shown in this video. We collect consistent annotations across frames, that is, objects are also tracked. In addition, we can also get labels for the semantic class of each object. In preliminary results, we tested a SailWAS 3D trained model, which only looked at the person class on a real video from the Davis dataset. We find that the predicted shapes are reasonable, even though the model is trained on synthetic data. I refer you to the paper for a quantitative analysis. I believe better results can be obtained, which is something that we're currently looking into. To summarize this part, I'd argue that models and data are getting increasingly accurate, but much more work is needed. And I want to conclude this presentation by summarizing the foundational AI research goals that we need to tackle across different thrusts within AIFARMS. The AIFARMS team identified 6 key AI problems which we think are holding back the use of AI and machine learning in the agricultural domain. To illustrate this, we use the picture shown on the right, where the 6 key AI problems are the root, the stem subsumes the use-inspired AI challenges, and the leaves are the desired ag outcomes. The 6 foundational AI research goals, which are certainly not only challenges for AIFARMS, are the small data problem, heterogeneous information fusion, integration of domain knowledge into machine learning techniques, federated learning at the edge, learning to control, and human-in-the-loop intelligence. The small data problem addresses the frequent concern that high-quality label data is often hardly available and extremely expensive to collect. To see this, imagine I were to ask you to annotate frames of a video like the one on the right, with bounding boxes highlighting the pigs. Despite impressive tools being available, manual annotation of thousands of frames takes quite a bit of time. Because of this, we need algorithms that can better get away with fewer annotated data. Our first research steps in this direction include development of novel semi and weakly supervised learning algorithms, new few-shot learning techniques, novel data augmentation techniques, and better transfer learning. In this context, please also check out work by my student Jason at CVPR 2021. A second foundational research goal, heterogeneous information fusion, addresses the concern that diverse and multimodal data is ubiquitous, particularly in the ag domain. For instance, we may record both video and audio data from pig farms, but devising algorithms which benefit from multimodal data is non-trivial. Our first research steps in this direction include development of novel regularization techniques, which encourage algorithms to focus equally on all available data, and novel techniques to identify data bias and flag if we are not using diverse data homogeneously. In recent work, team members also learned to generate visual dynamics from sound and visuals. Integration of domain knowledge into machine learning is particularly important in an ag setting. We cannot blindly trust an AI algorithm output, but we often need ways to understand why an algorithm made a suggestion, which helps to establish trust. Further, for many ag problems, we have domain knowledge at hand. Integrating this domain knowledge will help reduce the need for training data. A first step in this direction is research which designs predictors based on the structure that an algorithm detects in data. A fourth important research question that will facilitate adoption of the techniques which we develop is federated learning at the edge. Presently, machine learning training requires big data centers which aren't available on farms. To make matters worse, in rural areas, an internet connection may not be around either. Our first research steps which address this concern include development of networked ag bots which share information via local network hotspots and federated and streaming machine learning for navigation and perception across robots. The fifth goal focuses on learning to control. Presently, we often develop control algorithms in simulated worlds. We think the community needs to better understand how to bridge the real-world gap and how to learn more adaptive control mechanisms. First steps in this direction are our early work on multi-agent collaboration and adaptive control. Lastly, we think human-in-the-loop intelligence is another important aspect for adoption of AI techniques in the ag domain. AI won't replace humans, but will empower to focus on important aspects. First research in this direction includes development of methods for interaction between AI and humans, for instance, via language. Unfortunately, I don't have time to showcase all the impressive research that has already been done by team members in the last year. But I hope the few teasers highlight that addressing these 6 challenges is key to successfully advance AI in the agriculture domain. I hope that many of you are interested in following along or even helping to address some of the challenges that we're facing, not only within AI farms. So please reach out. With that, I thank my funding sources and particularly NSF and NIFA for AIFARMS, as well as all the collaborators and you for listening. Feel free to reach out with any questions that you may have, which I'm excited to answer. Thank you.